All right. Let me open the all right. And then within that, we've already finished the unsupervised learning. And after the completion of the unsupervised learning, we moved on to supervised learning. And as part of the supervised learning, we understood the concept of Y and X, all right, and the concept of input and output. And then we discussed about the shallow machine learnings. And then we discussed about the Bayesian classifier or naive Bayes learning. And as part of that Bayesian classifier, we did the multinomial Bayesian classifier, all right, that we had seen. We have seen the same thing in both R and Python. So that was something that we had done yesterday. And now we are going to move into some more classification models wherein we are going to know about the k nearest neighbor. All right, so that is what we are going to be doing. And scrolling down, we are going to be talking about the k nearest neighbor. This is going to be a relatively quick topic. We'll be able to probably move on to another topic as well while we are doing this. So let me start. All right. So as always, I will use the presentation available to me. Which is the same thing that is in the AI Sprite. All right. So k nearest neighbor classifier, and what is the meaning of it? So we have already discussed, we've already understood about the the concept of classification. All right. And now we are going to use another model for that. So we are going to use what is known as the nearest neighbor. Now take a look at this particular data. This is some scanned images I have. All right. These are some scanned images that I have. And these scanned images, now on purpose, I'm not recognizing this particular image. I know it is one. Everybody understands it is one, but we have to understand it in the perspective of a machine learning algorithm. All right. So here I'm going to classify this as A, B, X, some label ABX. This I'm going to classify it as CP4. All right. This I'm going to classify it as MD16. All right. This I'm going to classify it as C2D2, so on and so forth. Now there's a reason why on purpose I'm giving it a vague label. I'm not labeling it as 1, 2, 3, 4, 5 because I don't want the confusion to happen. Okay. And next, we are now going to identify these, excuse me, we identify these various what to say, the uh, uh, images. All right, I was about to say numbers, but I was controlling myself. Let us identify these various images as by its certain features. All right, now what we are going to do is we are going to get a new image which looks like this. Now we are going to take this image and do a comparison, a face-to-face comparison. All right, like when you have a photograph of a criminal and you want to see whether that person is similar or not, you compare that photograph with different faces. All right, so we have this particular image 4, and I'm going to compare it with all the images. Does it look like this? No, 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 no. When I take it here, this kind of looks pretty similar. With everyone else, it is not similar. All right. So when you look at this particular image is quite similar. Excuse me. This particular image is quite similar to this particular image. And we already know that this is C2D2. So therefore, this new image is also classified as C2D2. Now, it is a different story altogether that C2D2 means 4 or 4. So we are able to, do the identification. So what we have here is a scenario, all right? What we have here is a scenario of multi-class classification. All right. Now, in yesterday's class, we wanted to classify the data into only 2 classes, which is ham and spam. So it was a binary class classification. This is a multi-class classification. How many classifications you have? You have a total of 10 classifications. All right. We have a total of 10 classifications. And out of that, we are going to do the multi-class classification. Okay, so this is the basic premise of the k nearest neighbor. Now, how does it work? Let us try to look at this. Now, let us look at a binary class classification. To understand this, let me put a tabulation. All right, I'll put a small data. Let me open it in Excel. Okay. Now, I have 2 inputs. All right, I have 2 inputs, input 1 and input 2. And I have the output. So let us assume that I have the values 12, 15, 11, 7, 1, 3, 23, 20, 24, 14.8, 16.9, so on and so forth. I have some random data. All right, I have some random data, and let me increase the size here. I have the output. I have the output. What is the color? Pink and blue. Yeah, so pink, blue, blue, pink. All right. So this data, we have two inputs. So it is called a bivariate data. And in the output, we have two classifications. So binary classification. So this is called bivariate binary class. Now, if you have input 1, 2, 3, 4, 5 and two classes, it becomes multivariate binary class. You can also have, so let me write it down like this. You can have univariate, you can have bivariate, you can have multivariate. You can have binary class and you can have multi-class. So essentially what we are doing is we have univariate binary class, univariate multi-class, bivariate binary class, bivariate multi-class, multivariate binary class, multivariate multi-class. You don't have data with anything with a single class because single class output doesn't make sense. All right, a single class output doesn't make sense. It is simply, there is, I mean, when I say it doesn't make sense, there is nothing to predict with it. If all the people are doing engineering, let us say in a particular state, every graduate is doing the engineering course, then what is there to predict? A person who is currently finished his 12th standard, what course will he do? Do I need a model to tell me that it is going to be engineering? We all know that it is going to be engineering. All right, we all know it is going to be engineering. So there is no prediction involved. Only when it is this kind of scenario, we have the this thing. Now, I'll give you an example of, excuse me, I'll give you an example of univariate data. All right, let me take the next page. So I have the weight of the person, and weight class. 92 obese, 67 moderate, 44 underweight, 110 obese, 82 moderate, 36 underweight, so on and so forth. Now, there is only one input, but we are having three classes or multi-class. Is it clear, friends? Quick confirmation if you have understood what we have discussed so far. Do you understand the concept of univariate binary class? I have given the example of univariate multi-class. Bivariate is the example that you are seeing right here, where you have two inputs and you have two classes, pink and blue. All right, you can have bivariate multi-class also, and you can have multivariate binary class and multivariate multi-class. We will see examples of bivariate binary class, bivariate multi-class, multivariate binary class, multivariate multi-class. Some of them we'll see. What we will not see is the univariate binary class or univariate multi-class. That is something we may not see as part of our exercise, but the remaining two we will definitely see. All right. Okay, so we are going to have the attendance now. You have about 7-8 minutes to do it. Can you please post the attendance link? My colleagues, can you please post the attendance link? We are doing it early today. Like I said, it will be random. Please post the attendance link for everybody to see. Hello, can you please post the attendance link? Yeah, so there you have about 7-8 minutes. Yesterday somebody was saying that 3 minutes is too less. So 7-8 minutes is there for this particular attendance link. We'll discuss about multinomial and binomial at a later point of time. Right now, we are simply looking at the number of classes. What you're asking is about the order of the classes. No, I have posted the attendance link in the chat window. It has already been posted for everybody to see. You will not get it personally. It has already been posted. So people who have joined before 6:20 will be able to get it. Simple as that. We have given 20 minutes time for people to join. All right. Just post the attendance link once again, please. My colleagues, post it once again. And don't post it after that. That will be the last time. All right. I'm going to start the recording once again. Backend team, do not post the attendance link again. And anybody who is sharing the attendance link in the chat window will be immediately removed from the session. All right. So please do not share the attendance link later on. All right. If you do that, you will be removed. And anyway, this will expire in about 6 minutes. I think 5 minutes it will expire. So it will not be of any use. So let me proceed further. Now, temporarily, I'm going to suspend the chat. All right, because too much of discussion happened immediately after the attendance is given. A lot of discussions happen. So now no discussions can happen. People can come in, no discussions can happen. If there is a doubt or if I feel I need to ask you a doubt, I'll definitely enable it again. All right, I don't want discussions about this thing. All right, I'm going to restart the recording. So we were discussing about the univariate, bivariate, multivariate, that is the number of input values. One column of input is univariate. One column of 2 columns of inputs is bivariate. More than 2 columns of input is multivariate. All right. If the output class is only 2, binary class. If the output class is multiple, multi-class. All right. These are the two things that we have. Now, let us go back to this particular scenario. Now, this is a case wherein you have, okay, let me use this as an opportunity to, make you respond. What type of data is this? You are able to see 2 outputs and you're able to see 2 axes. So what type of data is this? Please respond in the chat. What type of data is this? You can only respond in the private message, so that's okay. What type of data is this? Excellent. Amongst the people who responded, very good. It is a bivariate binary class. This particular data is bivariate binary class, meaning I have two classes on the two axes. This is one, input one, and sorry, and this is input two. Input one, input two. Now, generally, the input one and input two are represented as x1 and x2. So, general notation is it is x1, x2, x3, so on and so forth, and you have the output y. All right, this is what we generally have. Okay, so this is a bivariate binary class. Okay, now based on this data, I want to do the classification. Now let me use a different color. Let me use green color. So I have a person, or I have a data point whose x1 and x2 values are such that the point is located there. All right, so what is the x1 value? So this is the x1 value and this is the x2 value. I think this much you must remember from the Cartesian coordinates in school. So based on the x1 and x2 value, this particular data point is where it is. Now, based on the concept of one nearest neighbor, that is, who is the person closest to this person? The closest is the pink dot. So therefore, this person is also, or this data point is also pink. Do you understand the concept of one nearest neighbor? Please respond. Do you understand the concept of one nearest neighbor? Perfect. All right, thank you. Now, this same dot I don't go by the one nearest neighbor. Why only one? I go by the two nearest neighbor. So who are the two people who are close to this particular data point? So the two people who are close to this data point are this and this. So if I were to put a circle around this, this is the two nearest neighbor. Now, there is a conflict. The conflict is that one of the neighbors says, you are pink. The other neighbor says, no, you are blue. So what should this new data point? New data point is the green. I'm giving it some color, so I'm giving it green data point. So what should the new data point do? He will say, okay, if there is a conflict, I will go with the nearest neighbor among the n neighbors. So n here is 2 or k neighbors. Nearest neighbor among the k neighbors. All right. So this one is again classified as pink. Do you understand the concept of two nearest neighbor and how when we are having two different classifications, we are going with the nearest neighbor? Did you understand that concept? I'll repeat it for the benefit of few people who have asked me. All right, I'll repeat it. Let me erase this. The pink and blue data points are the data points which are already classified, right? Like this. I have the input, I have the output, I have the input one. Let me now replace this x1, x2. I have this data. I have a lot of data, hundreds of records. Then finally, I have one record which is 17 and 28. All right, I have 17 and 28. Now I want to find out the output, but I want to predict the output. So this 17, 28 data point is, imagine for a moment, this green data point, the location of this. Now the output class, which is either pink or blue, is something that I need to do. All right, the output class, which is pink or blue, is something that I need to do. So I go with, oops, I deleted that. It's okay, no problem. I'll put it again. All right. So this new data point needs an address. Are you going to put it in the pink address or blue address? So if I go with the one nearest neighbor, this gets the address pink. If I go with the two nearest neighbor, all right, if I go with the two nearest neighbor, who are the two nearest to this, and this? So in this neighborhood of the two nearest neighbors, there are two people who are, and both of them are opposing colors. Now this person, this new person, this green person cannot be living in the blue house and the green house. So what we will do when we have such a scenario, go with the nearest among the two neighbors. So this is again declared as pink. All right, now let us go for three nearest neighbor. Somebody was asking how many neighbors we can go. How many ever you want, we'll discuss about that. So the nearest neighbors are 1, 2, I think this is the nearest by the distance. So if you were to put a circle around it, now you go with the majority. So now what is the address of this new data point, the green data point? The address of this green data point is blue. All right, because the majority among the three neighbors are blue in color. Therefore, this is blue in color. Is it clear? It is clear. Okay, perfect. Now let me answer the question, how many neighbors we can go. Now, before I answer the question, how many neighbors we can go, you please tell me intuitively. I will ask the question, I'll give the answer also. Do you agree with me that intuitively, if this is K, all right, K nearest neighbor is the name of the topic, KNN. So do you understand intuitively that more neighbors would mean more, all right, more neighbors would mean more accurate prediction? All right, more neighbors would mean more accurate prediction. Do you agree with me? So if I have a high value of K, that is, I am taking the inputs, rather than taking the input of one person or two person, I'm taking the input of many people, their opinion of many people, and I'm making them divide. All right, that is what I'm trying to find out. Is it clear? Perfect. So let us assume for a moment, before this data point came into existence, there were 100 data points. Now, for instance, yeah. So if you look at the serial number, all right, let us assume for a moment there are 100. All right, let us assume there are 100. Now, among the 100, so n is equal to 100 and blue is equal to 30 and I don't have a pink color, so I'm going to use red color. Pink is equal to 70. All right. Now, if I have a data point here, all right, if I have a data point here, and if I take the k value is equal to 100, then I am going to be taking the opinion of everybody, all the neighbors. So this value is going to be declared as pink because the majority is pink. Now this is okay. I'm simply going by the majority voting. But this is not a very good thing. Why? Because if my data point were to be here, now forget about k is equal to 100, forget about everything else. This data point here, we know for a fact that should be blue because everybody around it is blue. This is very clear. However, because we have taken k is equal to 100 and 70 numbers are pink, this fellow is going to be wrongly classified as pink. The point I'm trying to make is high value of k is good, but very high is bad. All right. The high value of k is good, but very high is bad. Is this clear? Is this clear? Please confirm, everybody. Now, which is the appropriate value of k? That I will tell you. Don't worry about, don't ask me that question, how to find out the correct value of k. That I'll help you with that. All right. But do you understand the premise? See, going with k1 or k2 is incorrect. All right. I'll give you another example. Let us say I've gone with k1 and my data point is here. Now, this green data point is more likely to be a blue color than a pink color. But because of k1, this becomes pink, which is wrong. If you have k is equal to 4, all right, if you have k is equal to 4, and in your 4 neighbors, let us say you have data point here. Let me give an example. K is equal to 4. Your data point is here. This is what it is. So you have to find out the nearest neighbor. So this is the nearest neighbor. So this data point is blue. If you have a conflict, go with the nearest one neighbor. All right. So the examples are pretty self-explanatory. Excuse me. The example here is pretty self-explanatory. 1 nearest neighbor, it becomes pink. 2 nearest neighbor, also pink. 3 nearest neighbor, it is blue. 8 nearest neighbor, it is pink because 5 pink and 3 blue. So therefore it is pink. All right. Once again, a quick confirmation if you all have understood, then we can jump into the next part of it. It is impossible. It is impossible to have exactly the same distance. But I have a solution for that also. Don't worry. Don't worry. I have a solution for that also. Okay. Thank you. So let's proceed further. So this is what the k values are. So if you keep increasing the k value, the model accuracy will increase, but after some time the accuracy will fall down. All right. So let us now look at a small example. This example is with reference to some type of food items. All right, we have apple, bacon, banana, carrot, celery, cheese, and much more. Now, these food items are classified into three major food types: fruits, proteins, and vegetables. And we have two input measures. All right, so we have two input measures, x1, x2, and y. So now, can you tell me what type of data this is? Can you tell me what type of data this is? Please respond to the chat message. Can you tell me what type of data is this? Very good. Very good. Very few responses, but all of them are most of them are giving correct responses. Very nice. All right. So this is bivariate. All right. This is bivariate because there is only two variables, and it is multi-class because there are more than two classes. Bivariate, multi-class. Perfect. That is the answer. Now, when I plot this data, this is how it looks. How sweet that particular food tastes, and how crunchy that particular thing is. So I think you can understand how apple is here, how lettuce or celery or carrot is here. All right. And cheese is neither crunchy nor sweet. Banana is very sweet, but not at all crunchy. All right. So this is what we have declared it. Now, when you look at this is how the classification is done. So almost all fruits are sweet, and they can be anywhere from zero crunch to high crunch. Proteins are generally less sweet and less crunchy, and vegetables are generally crunchy and can be from no sweet to slightly sweet. Is this clear? Is this clear, my friend? Please respond. Is it clear? Perfect. Thank you so much. Now we have the tomato coming into the picture. All right. We have the tomato coming into the picture. Now this tomato, based on the one nearest neighbor, where will you fit him? Based on the one nearest neighbor, where will you fit the tomato? It is closest to, I think, the grape. So tomato is a fruit. If you go by the two nearest neighbor, I think these two are the closest. Now, once again, you have one protein, one fruit, but grape is closest. So again, it is this thing. Three nearest neighbor will make it. Two of them are saying fruit. One of them is saying protein. Again, fruit. If you go with the four nearest neighbor, two fruits, one vegetable, one protein. Again, tomato is a fruit. So therefore, we can call tomato a fruit. Yes or no? Can we call tomato a fruit? Even Google says tomato is a fruit. Do you know tomato is a fruit? You can Google that later on. You can find out why it is a fruit and all those details at a later point of time. But tomato is a fruit. All right. So we have this. Now let us go ahead and work with the coding part of it. So I'm going to open a code. Let me just close the other things that are not there. Yeah. So let me clear this up also. Or let me just close this once and then open it again. Yeah. Good, good. Many people know that tomato is a fruit. Very good. Yeah, it is. If you have a clear majority, doesn't mean this thing. If all that is only it's always majority. Very simple. All right, it is always majority. Only if there is no majority, it go with the nearest neighbor. So I have a data set called WBCD, which stands for the breast cancer database. All right. So I have this database which is called the WBCD database. I'm going to open that. All right. Now there is something called as the diagnosis. There is a patient ID. So we have 569 records. All right. And we have 32 variables, 32 columns. So the first column is, of course, something that you can ignore. All right. The second column is the output. Remaining 30 columns are the input. All right. The remaining 30 columns are the input. So what I'm going to do is the patient ID is something I don't need. So I'm going to remove the column 1 and reassign it to WBCD. So when I do that, I have removed the patient ID. Now I am going to look at the table WBCD $diagnosis. We have already seen these kind of commands. So what are all the values within diagnosis and what is the count? So if you look at that, you have 357 cases of B and 212 cases of M. Now let us do another Google study. What is meaning of benign? Benign refers to a condition, tumor or growth that is not cancerous. It means that does not spread to other parts of the body, does not invade nearby tissue. Sometimes condition which suggests that it's not dangerous or serious. All right. So a person may have a benign tumor, a person may have a malignant tumor, malignant or malignancy, which is abnormal, divides without control, can invade nearby tissue. So basically, malignancy is the cancerousness. So there are certain tumors that have been diagnosed under this WBCD database. All right. They have done some non-invasive study. I know you are all engineering graduates, none of you are from medicine, but it is always good to have some general knowledge. So non-invasive diagnosis or non-invasive study is when you do the scans, x-rays, all right, ultrasound, all those things are non-invasive study. So I have done probably some ultrasound, some scan, etc., and they have signed the radius, the average radius of the tumor, texture, perimeter, blah 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 blah, etc., etc., etc. So many things they have measured. All right, so many things they have measured as part of that particular tumor, and they have identified it to be either benign or malignant by an invasive method. What is an invasive method? You will have to pull out a piece of the tumor. You will inject into the tumor. You will take a small piece of tumor and then you will observe it under the microscope, and then you will see whether the cell division is very rapid or slow. I mean, is it happening very rapidly or it is normally happening? That is what you will be doing as part of the study. All right. So we are manually classifying them as benign and malignant. All right, something similar to what we have done here. We have scanned these images and we have manually classified them as A2, B3, CPC4, C2D2, etc., etc., knowing that I know that these are all 1, these are all 2, these are all 3, these are all 4. Is it clear? So the human being has made the classification. For these 1, 2, 3, 4, 5, 6, 7, 7, 5, 35 different images. Now with these 35 different images, the 36th image that we got, which was this, without the human being, we could classify it as it is neighborhood to this particular image, and this image is classified as FOUR or 4. Therefore, the classification happened. So that is exactly what we are trying to do here. For 569 cases, we have done the prediction using, for 569 cases, we have done the prediction using the manual or the invasive method of biopsy. Some of you may know what a biopsy is, some of you may not, but biopsy you can Google later on. Using a biopsy. Now I want to avoid the invasive method. So in future, if the 570th patient comes, I will subject that patient to the scan. That scan will give me all these 30 inputs. And on the basis of these 30 inputs, I want to predict, I want to classify that particular tumor as whether it is benign or malignant. All right, is the business problem clear? Quick confirmation, friends, if the business problem is clear. One record is 1% data, absolutely right. Multivariate binary class. So this is a multivariate binary class, and one record or one row is 1%. All right, now we are going to look at the structure of the WBCD dollar diagnosis, and you look at it, it is a factor with levels B and M with 1, 1, 1, 2, 2, 2 like that. All right, it is this particular value, we have got it here. And biopsy is a measurement, which is, you can Google it. All right, what is a biopsy? Okay, so what I'm going to do is I'm going to manually classify, I'm going to manually, I'm not sorry, not manually classify, I'm going to further define this particular diagnosis as a factor variable, knowing pretty well it is already a factor, but also I'm going to give it labels which is benign and malignant. All right, I want to give it a label which is benign and malignant. So therefore I'm going to say diagnosis factor. Okay, now if you look at line number 9, you will see this with 2 levels, benign and malignant, 1, 1, 1, 2, 2, 2, like that it will be. Okay, now if I want to also look at the proportion, you can look at this into 100. So 62.74 and 37.26. Now what does it tell you about the data? This proportion, what does it tell you about the data? With reference to something that we have discussed in the previous class. What does it tell you about the data? Very good. Excellent. Excellent. Very few people have responded, but you are getting the hang of it. This data is not imbalanced. All right. This data is not imbalanced. It is not imbalanced. The output classes are less than the 70-30 split. Okay. Now we are going to look at the we have not yet gone to the test data. I didn't understand your question, but to tell you, we have not yet gone to the test data. The train and test concept, the part of it has not yet come. The 30 columns are input data. All right. The 30 columns are input data. Anybody else facing the voice breaking issue at my end? Please respond in the public chat. Yeah. So whenever somebody mentions voice breaking issue or something like that, I request others to respond in that. No, it is fine for me or things like that. So therefore that person may. Okay. All right. So now, ideally, we are supposed to look at all the columns. All right. We are supposed to look at all the columns and we are supposed to perform what is known as, let me just go here and show it to you. I hope all of you are viewing this mind map, but if you are not, then probably I will give you a lesson once again. You are supposed to perform EDA, exploratory data analysis. You are supposed to look at the various parameters. You are supposed to look anytime you get a data, whether it is for unsupervised learning or supervised learning, you have to perform the exploratory data analysis. First, second, third, fourth, you have to probably even do the graphical representation. Now, these things, I'm not doing it repetitively for every data because it is something you have already learned how to do it. So therefore, I expect you to do it. All right. Just because I am not doing it in the code doesn't mean it is need not be done. All right. So it is expected that you perform the EDA. All right. Now, because there are 30 input columns, I'm not going to do the EDA for all, but I am going to definitely do the EDA for a few of the columns. I'm going to select randomly column radius mean, area mean, smoothness mean, and look at the summary. All right, and look at the summary. So this is what I have here. Now, if you look at the summary, you are able to see almost all the moments of business decision. All right, you're able to see almost all the moments of business decision. You have the min and max, you have the mean, you have the median, you have the first quartile, third quartile. In fact, if you look at this values, let me just show you. If you look at these values, you should be able to visualize mentally the box plot also. Now we'll come to that at a later point of time. We'll give it some time. Right now, we will continue with the KNN. Now, how to visualize the box plot from this data is something that we will see at a later point of time. All right, but we have to do this. But the thing that I want you to observe is when I'm doing this visualization, this summary is that I have single to 2-digit values for radius mean, 3 to 4-digit values for area mean, and decimal values with the maximum of 0.16 for the smoothness mean. So there is a problem of scale. And we have already seen that when there is a problem of scale, it can affect our distance measure. We have learned it as part of the k nearest neighbor. All right. So we do the normalization, absolutely right, or standardization. So for that, we are going ahead with a function which is x minus min by max minus min. This is also something that you are already aware. You're already aware about these things. So I'm going to create a user-defined function which is normalize. Now, if I were to apply this normalize function to 0.01, 0.02, 0.03, 0.04, and 0.05, I will get this particular value. All right. And when I do the same thing for, see here, 0 to 1, it is normalized into 0 to 1. Okay. And then when I do this for 10, 20, 30, 40, same thing, I'll get the 0 to 1. Now this normalize function, I am going to apply it to the WBCD database from the column number 2, because diagnosis I'll have to ignore, from column number 2. So column number 2 to 31, apply the normalize function, convert the output into a data frame, and then put it into WBCD underscore n. Now, when you look at the summary of WBCD underscore n and area mean, remember the area mean was, 3-digit to 4-digit number. Now, when I'm going to look at the area mean of the WBCD underscore n, what is n? The normalization using the x minus min by range, or which is normalized to the range of 0 and 1. When I do that, you have the values ranging from 0 to 1. So the job has been done. Now, I am going to split the data into train and test. The concept of train and test you understood yesterday. Section 1, section 2. If you do not remember train and test, remember section 1, examination section 1, examination section 2. Now, don't quote me in your interviews that it is like section 1, section 2, because that interviewer doesn't know. He may not be my student. All right. But this is for understanding. All right. So I am going to take 469 rows and all the columns into WBCD underscore train from this WBCD underscore n data set. Similarly, from 470 to 569, which is 100 rows, I'm going to take for the test. All right. So I have the inputs, all the inputs for train data. I have all the inputs for the test data. Now, I also need the outputs for the train data. All right. The output for the train data is the first column in the WBCD database. Remember, your WBCD n does not have the output. It only has this. All right. So we are going to take that up. All right. So I'm going to take the inputs, the first 469 rows, and first column as WBCD underscore train underscore labels, and the 100 rows, the last 100 rows, and the first column as the output for the test data. All right. Just you can take 98, you can take 97, 80, 20. Generally, it is 80, 20, 75, 35, 70, 30. In that proportion, it is split. The proportion of the train data should be more than the proportion of the test data. All right. So it is time. So we take a break. All right. We'll be back. All right, so let us now continue. I'm going to restart the recording. So we have the input values, the 30 input values, I should say it correctly. We have the 30 training input values, the 30 rows of training input, 30 columns of training input values, which is 469 rows. We have the 100 rows, 30 columns of the test input values. We have the one column and 469 rows of the output y, which contains two classes. And similarly, we have one column of 100 rows of the test output y, which again also contains two classes. So now we are going to load a package called class. All right, this is the class. And we are now going ahead and performing the KNN. Now, for explaining this KNN, I'm going to briefly turn on my webcam, all right, so that you can probably understand it better. So we have the WBCD underscore train underscore data. We have the WBCD underscore test data. We have the output of the WBCD underscore train, which is the Y. We do not have the output for the WBCD test. So now try to imagine we have in this WBCD underscore train 469 records. Now these 469 records are going to be placed. Now between my two fingers, imagine I have a data point, I have a data point, I have a data point, I have a data point. Like that, I have multiple data points. Now these data points are in a 30-dimensional space. Now it is difficult to imagine. You can imagine 2-dimensional space on your computer screen. You can imagine a 3-dimensional space, in your room. Your room is a 3-dimensional space, length, width, and the vertical height. Now extend the logic to a 30-dimensional space. So each data point is defined by x1, y1, z1, t1, q1, p1, a1, b1, c1, like that. There's another data point is defined by x2, y2, z2, t2, q2, p2, ab, a2, b2, c2, so on and so forth. Like that, I have the data in a 30-dimensional space. So each of these data are sitting in that particular different places. All right. And I also send the labels. So each of these data points, on top of them, benign, malignant, malignant, you have the labels also available. Now these WBCD underscore test, which is the 100 test data points without the labels, are sitting with me. Now I send the first test data point. Now this test data point is defined by 30 variables. So it will go to its address. So it will go and then sit here. Let us assume this is the location for the test data. Now remember, this particular data point does not have a label. Now I'm saying, look at 21 neighbors. So this particular data point is going to look at 21 neighbors around it. All right, 21 neighbors around this data point. Now, among these 21 neighbors, there's going to be a majority. Let us assume there are 11 benign and 10 malignant neighbors to this test data point. So this test data point becomes, how many benign did I say? 11 benign and 10 malignant. So this becomes benign. So the first test data point becomes benign. It has been classified as benign. Now, the second data point comes and sits here. All right, it comes and sits somewhere here. Now this second data point will now look at 21 neighbors around it. Among the 21 neighbors, let us assume 15 are malignant and 6 are benign. So this becomes malignant. So the second data point of the test becomes malignant. Like that, all the 100 data points are given their classifications with respective 21 neighbors. Is it clear, friends? Please confirm if you understood. It is always going to be with the neighbors. Obviously, you can define the neighbor. All right. See, we are always looking at one test data point at a time. All right. We are looking at, yeah, Euclidean distance. You already have learned about the Euclidean distance. And you also know about the Euclidean distance in the perspective of multidimensional space. We've already seen that with the 6-dimensional space. Am I correct? We've already seen that with the 6-dimensional space. Clear, everybody? Okay, people are sending me private messages to inform you attendance is done. All right, I'm just informing everybody attendance is done. Please don't send private messages. Okay, let me just post it here. Yeah, let me not be disturbed henceforth. Mohammad Rafi Sheikh, you are having your webcam on. Okay, he's turned it off. All right. Now, the question about 21. 21 is some number that I have taken. All right, some number that I have taken. Now, after this, after I execute this, I will get the WBCD underscore test underscore PRED, the outcomes. When you look at this, this is what the predicted values are. All right, the 100 values, benign, malignant, benign, blah, 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 blah. The 100 test values we have. Now, I'm going to create something called as the confusion matrix for the test data. All right, I'm going to create something called as the confusion matrix of the test data. What is confusion matrix? It will take maybe 2-3 more classes to understand, but just take it for the time being. So I'm going to create a table on the x-axis with the WBCD underscore test underscore labels. On the y-axis, we have WBCD underscore test underscore PRED. All right. So I am going to now create that and save it into something called as confusion underscore test. And when I look at this, this is what I have. So how to interpret this data? We have 61 benign matches. We have 37 malignant matches. We have 2 mismatches wherein it was originally, so Y is the predicted. So this is predicted. This is actual. All right. It was actually malignant but predicted as benign. So this is very good. 98% accuracy with a 2% error. All right. With a 2% error. . Now I want to improve this particular accuracy. All right. I want to improve this particular accuracy. So what I'm going to do is I am going to try and change sorry, this was the test accuracy, right? My bad. This is the test accuracy. What about the training accuracy? So how to find out the test accuracy? You can manually say it is 98%, but if you want to do it through a code, the diagonal of the confusion dot underscore test divided by this sum of the confusion underscore test. When I do that, I get 0.98. Now, whatever explanation I had given by showing you my hand and the between the tips of my fingers, the same thing. We are going to remove every data point. I'm going to remove from, let us say, the first data point in the training data. I'm going to remove the label and then ask that data point to consult with 21 neighbors and find out what is the output. So temporarily asking the training data to ignore its existing classification and go with the 21 neighbors. All right. So that is what I'm going to do with train data. And here again, I'm going to do train itself, WBCD underscore train. All right. So when I do this, do the confusion train, we see here we have 13 plus 1, 14 incorrect predictions out of 469. So if you look at the accuracy, you have 97.01. So 97% is the accuracy. Pretty good. 98, 99. All right. Okay. So now what we are going to do is we see that the accuracy is good, but can I improve upon the accuracy on the basis of some other function? Now you remember the function of x minus mu divided by sigma gives me the z value. You remember this? This is called the z transformation. All right, this is called the z transformation. Z score, yes, Z score, Z transformation. So this command scale will simply take care of that. It will take the Z transformation. All right, it will take the Z transformation. So I am going to apply the WBCD -1, meaning except the first column for all the columns. What is the first column? It is the output. Do the Z transformation and put it in WBCD underscore Z. Now remember the area mean, which was 3-digit to 4-digit. Now when I do the summary using the Z transform data, you have this value. All right, you have this particular value. Okay. Now this WBCD underscore Z, I am now going to assign the first 469 records to train. So train already contained the 0 to 1 transformation values. Now I'm going to put this, and for the test I'm going to put this. Now remember the output is still the same. The y values are the same, that nothing needs to be done. So this command, which I've already executed, all right, this command which I've already executed, there is no change in the command except that the data within WBCD underscore train and the data within WBCD underscore test is modified. Is it clear? So when I execute this, I get WBCD underscore test underscore PRED, a new set of values. Now I can do the same thing, which is create a confusion matrix, but we can also do something which is called a cross tabulation. And for the cross tabulation, I need a package called Gmodels. So Gmodels is a very interesting package, all right, for model fitting. And using the Gmodels here. So this confusion underscore test, this table doesn't meet the Gmodels package. All right, so you can do the confusion tests. So what is happening now? The accuracy when I'm doing the Z transformation is becoming worse. In fact, the 0 to 1 transformation, the accuracy was better. All right, it was changing. So in fact, I feel that the 0 to 1 transformation is better. So let me also look at the cross tabulation, how it appears. This is how the cross tabulation appears. All right, a little more detailed way it is going to give the value, same thing. So the amount of misclassification is 5, therefore it is a problem. So what I will do now, I will roll back to the 0 to 1 transformation. All right, I will roll back to the 0 to 1 transformation. So once again, this values will be taken like this. All right, once again, the values will be taken like this. And now what I'm going to do is, I'm going to run this model. Let me increase the size. Let me put it slightly on top. Let me also reduce the size a bit so that it is visible in one shot. So here I'm going to run this model with k is equal to 1 and then look at the cross tabulation. So obviously cross tabulation is not visible. So if you look at this, what is the, if let me just make a note here. All right, k is equal to 1, error is equal to 4. Then when k is equal to 5, all right, when k is equal to 5, the amount of error is equal to 2. Then k is equal to 11, the amount of error is equal to 3. Sorry. Then k is equal to 15, error is equal to 3. All right, k is equal to 21, you already know. And then finally, I have k is equal to 27 and there's no place, so I'm writing it here, 27, 4. Now, if you look at this, it is slowly increasing and reducing. Is it clear? So for different values of k, it is slowly increasing and reducing. Okay, clear everybody? Okay. So today we are doing something different. I am going to take the attendance twice and I'm going to choose randomly whichever, either the first attendance or second attendance. It is your luck. So if you are a genuine person and you have attended in both the sessions, you have nothing to worry. So team, please give the second attendance link. All of you, please sign your attendance again. Remember, please remember, this is an entirely different attendance link. All right. Now, obviously, I may decide to take the trouble of matching the two. All right. If there are two entries, then you will get attendance. If there are not two entries, then you will lose the attendance. Is it clear? Or I may decide to take the first one, or I may decide to take the second one. So people who have given their attendance in both the links should not have any problem. So I'll have to come up with more and more innovative ways to counter the problem of the what shall I say, some of them people trying to fraudulently trying to take attendance only for the certificate. I hope you are are not too offended by making you do this again. Please fill up quickly. Is it all right, friends? I hope all of you are clear. People, the regulars, the people who are very regular about it, you are going to give your attendance, right? No, random timing also I'm going to do. That is also random only. This is also random. Today I gave 2 times. Tomorrow I may or may not give 2 times. So there should be an element of surprise, right? Now, if I give tomorrow attendance at 6:30, people will leave. Like today they have left. We had about 160, 164 people when we gave attendance. We only have 140 people now. See, people who are sincere, who join at 6, 5, 6, 10 maximum and attend the full class, you should have no problem. And it is for you people only that I want to give the certificate. There are a lot of people who hide behind the excuse of network issues, hide behind the excuse of I was there just during the thing, I went out and I came back, all those things. All right, some may be genuine, I agree. Some of you may be genuine, but I'll have to look at it in the overall picture. I don't know you, anybody personally, right? That I'm against you or for you. So I'm going to treat everybody in the same way, right? So all of you, please give your attendance. Today we are going to have 2 attendances, and one of them or both of them will be done, taken into attendance. All right, it expires in about 2-3 minutes. So yeah. All right, let me continue. All right. So now we have established it. Let us look into a slightly more detailed way of finding out the correct K value. All right. So what we'll do is we will create some values and we'll create a visualization. All right. We'll create a visualization. So I'll just run through this entire thing. I will not explain it line by line. All right. The output is something that is more important. How it is working is not important. So I create a predict train, predict valve, error rate, all these things. I create something. Then I am going to run this loop. I'll just explain in principle, not in detail, in principle what this code is doing. So for k values 1 to 39, I'm going to run this particular code. All right, for k values 1 to 39, I'm going to run this particular code. And I'm going to every time take the KNN and I'm going to take the accuracy values. All right, accuracies and error values. So this is one thing that I have done for 39 values. And then I'm going to take the error values into a data frame and the accuracy values into a data frame. Now using a package called ggplot, ggplot2 in fact, I'm going to now create a visualization, all right, an error plot with all these values. All right, so error plot is going to contain the contents of this, accuracy plot is going to contain the contents of this, and those two I'm going to plot it here. So this is how you have the plot for the accuracy. All right, okay, you have the plot for the accuracy and you have the plot for the error. Now if you zoom it up, all right, if you zoom it up, this is what it is. So K1, the error is very high, then it comes down. All right, let me first do it for the accuracy. All right, it is kind of giving the same value. Some issues are there. Let me use the error plot itself. Some mistake, maybe I'll look into it later. So let us look at the error plot. So error is, we have a maximum error of this value, then it goes down, it goes up, goes down, goes up, goes down. All right, so the lowest it can come is somewhere here. So probably this is the ideal k value. So 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So 21, 22, 23, 24, 25. K is equal to 26 seems to be a good value where the least error is obtained. All right, so using this visualization, you can choose the ideal k value and then that can be used for prediction of future values. So this is the method. This is the method that we use for identifying the best k value. That was something that was asked in the beginning of the class. All right, that was something that was asked in the beginning of the class. So let me now do the spider. All right, yeah, I seem to be having some issues with my laptop. Let me see if I can fix it. Too many things are open. Let me close it one by one and let us hope it improves. Just give me a minute. See, the bottom thing is not visible. I don't know what happened. Let me close the RStudio also. Too many things were open. Probably that is why the RAM was a bit less. Yeah, let it open. Just give it a moment. Yeah, I guess. Anyway, you understood the logic behind the. You've understood the logic behind the. Behind it. Yeah, 1 minute. So I'm just waiting for it to open up. It has opened up. Good. So let me start. Oh, I closed this thing. It's okay. Yeah. Now I'm going to take the k nearest neighbor classifier and load it here. Okay. So let me increase the size. When I open the pandas and the NumPy, and then I'm going to load the WBCD database. All right. Now, under the diagnosis, wherever it is B, I'm going to change it as benign. All right. And wherever it is M, I'm going to change it to malignant. Now, what I'm going to do is I'm going to take all the rows and columns 1 to 32 and exclude the 0th column. I hope you understand the concept of 0th column in Python. All right. So that is done. Now I'm going to create a function which is x minus min by range. All right. And we have created the function. We have a question here. Optimum k value is based on the 27 on the training data. No, it is based on the test data. K1, we train it on the test. We K1 for train and then the test. K1, K2 for train and the test. K3 for train and the test. K4 for train and the test. So it is ultimately based on the test data. All right. That is the answer to the question. All right. Coming back here, I have created this function. Now I'm going to run that function on the WBCD database from the first column, ignoring the 0th column. The 0th column is the output. All right. So I execute this. And then if you look at the describe function, it is obviously not going to show everything, but we know for a fact that it is all 0 to 1. All right. Describe is equivalent to your summary. Now I'm taking the values. All right. WBCD underscore N. I'm taking it into X. All right. I'm taking it into X, and only the diagnosis value in WBCD I'm taking it into Y. All right. Then we all know about the train and test split. So model selection is something that helps us in the train test split. We have seen that yesterday. Now, yesterday, when we split the data, we were able to split it and get two outputs. Now, if you give two inputs to this command, X and Y, and say 20, you will get four outputs, X train, X test, Y train, Y. So the first alphabet, X, will be split into X train and X test. The second Y will be split into Y train and Y test. So when I run this, you will get 4 values here. All right. Now I'm going to import something called as K neighbors classifier. All right. And I'm going to perform the K neighbors classifier on 21 neighbors, which we have done the same thing, straightforward. So KNN is an object that is defined to run the K neighbor classifier for 21 neighbors. Now when I run this on the X train and Y train, that is input and output, then we are going to have the KNN to predict on the test. All right. So on the X test, that is inputs of the test data. And if you look at it, this is what you have. The 100, how many values are there? 114, because it is not exactly force this thing. So it is 80-20 split. So what we did was probably 75, sorry, not 75. It was slightly less than 80-20 split. All right. So we have the outcomes here. Now we want to evaluate using the accuracy score. So we have something called the accuracy score. This is also something that we have seen yesterday. All right. And we look at the accuracy score between the Y underscore test, which is the output Y, and the PRED, which is the predicted Y. So when I execute this, 98.24 is the attendance, I'm saying attendance, accuracy, my bad, is the accuracy that I get for the test data. Now, if you want to look at the cross tabulation, same thing, you get it here, 68, 44, 2. There is 2 mismatches. All right. Now, if you want to do the same thing for the train, so run the KNN model on the X train. You run the KNN model on the X train, you predict it on the X train, and then look at the accuracy, 96.26%. Look at the cross tabulation, you have this 17 misclassifications. All right. Now, I am going to create, once again, we have not yet discussed about the concept of overfitting, so don't worry. We will, when we discuss about overfitting, I'll come to that. What about the chance of getting 100% accuracy? You may get it. You may get 100% accuracy. All right. Now I'm going to create an empty list variable called ACC. Now I'm going to run this for values from 3, 4, 5, 3, 5, 7, 9, etc. all the way to 49. So 3, 50, 2 means starting from 3 up to 50, not including 50, skip of 2. All right, skip of 2. So when I do this, the first time it is going to take the value 3, it is going to do the K nearest neighbor classifier with 3. So ni is going to be defined. So ni dot fit X train Y train, we do it. Then we do the train accuracy, and then we do the test accuracy. And then the train accuracy and test accuracy, I'm appending it to ACC. All right, I'm appending it to ACC. So when it runs for this loop, I'm going to get 2 columns of data, train accuracy, test accuracy at 3, train accuracy, test accuracy at 5, train accuracy, test accuracy at 7, train accuracy, test accuracy at 9, train accuracy, test accuracy at 11, so on and so forth. So let me now execute this. All right, let me now execute this. ACC is not defined. Did I not execute this command? Maybe I did not, maybe I forgot. So now let me execute it, and then I'm going to run this loop. So it takes some time because it is running so many k nearest neighbor classifiers. All right. Now I'm going to take this matplotlib pyplot from PLT for the visualization. Now I'm going to plot 3 to 50, skip of 2, I0. I0 meaning the first column. So I in ACC. So what is the 0th column in ACC? The 0th column in ACC is train accuracy. So when I execute this, you have a plot, and this is the plot. Now without closing this screen, on the same screen, I am going to plot I is equal to 1. What is I is equal to 1? This is the test accuracy. So when I look at this, this is the plot. So red is the train and blue is the test. Now, all right, we have the outcomes here. So this is an accuracy plot and not an error plot. So which place do we get the maximum accuracy? We get the maximum accuracy for the train data at this point. Then the accuracy wanes, and after that it is all the same. All right. So it makes sense for me to have k value is equal to 20. Is it 20? Is it 20? It cannot be 20, it will be 19 because we are skipping. Now, in this code, somebody was asking during the, the session, what if I have exactly equal? Somebody asked me, what if let me just plot it out. I have 1 red, 2 red, then I have 1 blue, and let me make it slightly better. And the new data point, which I'll put in black color, is here. Now, if I say k is equal to 4, and if I have these 4 neighbors, then there is a conflict. There are 2 people who say the black data point should be blue, and there are 2 people who say the black data point should be red. And when I look at the measurement, I find that this measurement and this measurement is equal. So what do? This will create a problem. To avoid this problem altogether, when I have binary class, I don't keep even neighbors. If you have binary class, don't keep even neighbors. Something similar to the single bench, or if you remember the the jury system. All right, the jury system in the country, it was there previously, it was no longer there. In America, it is still there. The jury is always an odd number. So it should never happen that 10 people say guilty, 10 people say not guilty. It should never happen. Do you understand? So it is always an odd number of people. Now, what if the output class was, I have red data points, I have green data points, I have blue data points. So what is the number of neighbors should I keep? What is the value of k should I keep? What is the logic you feel? What is the number of K should I keep? If I have a multi-class and there are 3 classes, if I keep odd, if I keep very smart, excellent. I was hoping many of you would say even. So keep even 2, 4, 6, 8. Now 2 is okay. But what if in 6 you have, what if you have 6 neighbors, and in that 6 neighbors you have 2 green, 2 blue and 2 red? Again a conflict. So choose the number of neighbors which is not divisible by the number of classes. Simple logic. So you take 2, 4, 5, 7, 8, 10, 11, 13, 14, 16, 17, 19, 20. You can take both odd and even, but it should not be divisible by 3. Isn't making sense? Please confirm if you have understood, friends. Do you understand why? So do not simply go by just because in even classes we are taking odd neighbors. So in odd classes we'll take even neighbors. No, don't go by that. Is it clear? All right. So these are some logics, and these are very simple tools or very simple applications for, performing the classification modeling. All right. The codes are available in your AI Spry account. If they are not there, then please let us know. We will have it added into that. All right. And as I expected, the number of people have stopped coming down. So I'm guessing there are about 120 people who are sincere about their lessons. Yeah, prime number is better. It is not divisible by anything, but prime number is very limited. The number of prime numbers is limited. There can be a number in between. All right. There can be a number in between. Can you explain what? I'm sorry, what you want me to explain? The entire KNN? No, it will not be possible to explain the entire KNN in just 3 minutes, 2 minutes that I have. How to find the value of K? Okay, fine. I'll explain that. By the way, the data sets are available in the AI Spray. All right, it is available in the AI Spray. So here, the maximum value of accuracy, this is 0.97, 98, 99, and this is 100%. So you have 97, 98, 97, 98. So this particular value, this is where we first got the high accuracy. Now remember, taking a very high, I can also take K41, K47, but K47 means every data point has to talk to 41 neighbors. It is going to make the process slow. So ultimately, the objective should not be to make the system very slow. You're talking to 41 neighbors and then deciding the output. If I talk to 90 neighbors also, it is going to give me the same value. So I choose in this particular visualization the point where I first get the highest accuracy. All right, the point where I get the first highest accuracy, which is at 19, because I cannot have 20 because I have only the odd values in my data. In my loop, I have taken only the odd values. So 19 is the value which is going to give me the highest accuracy, and therefore when a new data point comes, a new cancer patient comes whose tumor details are given by those 30 values, I will take that new data point, talk to the 19 neighbors of that new data point, and do the classification. That is what we do. Are we good? Is your doubt clarified? Is your doubt clarified? You can stop going live, my colleagues. Please stop going live. YouTube live can be stopped. Our session is over.